Oftentimes, the region of integration of an iterated integral need not have any straight lines as boundaries. If we look back to the previous example, that's exactly what we had when we were looking at the area bounded by the sine and cosine curves. The region of integration from the previous example is vertically simple, even though it has no vertical lines as left and right boundaries. The quality that made the region vertically simple is that it is bounded above and below by the graphs of functions of x. One order of integration will often produce a simpler integration problem than the other. However, the answer will always be the same. That is, the order of integration affects only the ease in which the integration is done, not the actual value of the integral. So at the end of the day, if you look at a region that has a well-defined area, that area is going to be the same no matter which manner in which we go ahead and compute it. To illustrate this, let's take a look at the region given in example 5 by the iterated integral from 0 to 2 from y squared to 4 dx dy. Let's go ahead and sketch this region, see what it looks like. We'll compute this iterated integral, and then we'll switch the order of integration and show that we get the same answer if we do the order in the other direction. So instead of doing dx dy, we will also set up a iterated integral to calculate the area of the region by using the order dy dx as well. So first things first, let's kind of go ahead and take a look and see what we're working with here. If we look at the outermost bounds, this region is going to be bounded for y between 0 and 2. So I know y is going to be bounded between 0 and 2. And if we look at the x bounds, x is going to be bounded by y squared and 4. Well, here's 4. And if we were to look at the equation x equals to y squared, that actually would be a horizontal parabola that would look like this. So x has to be between 4 and this horizontal parabola. So this is what we would be looking at. So this is our region R. Let's go ahead and compute the area of this region. This is going to be equal to the definite integral from 0 to 2. The antiderivative of 1 dx is going to be x. We would then evaluate that from y squared to 4. This is going to be equal to the definite integral from 0 to 2. Evaluate x at the upper limit of integration. Subtract x evaluated at the lower limit of integration. And we get this. We can now go ahead and find the antiderivative of 4 minus y squared. That should be 4y minus y cubed over 3, which we're going to evaluate from 0 to 2. Substitute in the upper limit of integration. Subtract that antiderivative evaluated at the lower limit of integration. And this should produce 8 minus 8/3. This whole second part is going to be 0. If you get a common denominator, 8 minus 8/3, that's going to be 24/3 minus 8/3, which would be 16/3. Okay. So when we do the order of dx dy, we calculated the area of the region, and we found that it was going to be 16/3. Let's go ahead and redo this problem. But now we want to switch and do a different order of integration. So let me go ahead and set up my representative rectangle. So we're going to now look to try and do it in the order of dy dx. if we look at our outer bounds for the x variable, x is going to be between 0 and 4. So it's going to be 0 and 4. And now if we look at the bounds for the y variable, y is bounded below by the x-axis. That's y equals to 0. And it's bounded above by this curve. Well, we know from before that this curve has the expression x equals 2 to y squared. But whenever we're trying to set up an integral dy, what we need here is we need for this to be a function of x, meaning we have to take this y and get it by itself. If I take the square root of both sides, we would get that y equals the square root of x. Technically, when you take a square, get rid of a square, we have plus and minus, but we only have the upper half branch of that horizontal parabola, so it's just a positive square root of x. So this is what the iterated integral would look like for the area of that region with the order dy dx. Let's go ahead and compute it. This is going to be the integral from 0 to 4. The antiderivative of 1 dy is just going to be y. We're going to evaluate that from 0 to the square root of x. This is going to be the definite integral from 0 to 4. I'm going to have the square root of x minus 0 dx, which is equal to just the integral from 0 to 4. Rewrite it as x to the 1/2 dx. You can find the antiderivative, add 1 to the power. 1/2 plus 1 is 3/2. Divide by that new power. Dividing by 3/2 is the same thing as multiplying by 2/3. And now we're going to evaluate that antiderivative from 0 to 4. This is equal to 2/3 times 4 to the 3/2 minus 2/3 times 0 to the 3/2, which is equal to 2/3 times the 3/2 power is a combination of a square root and a cube. The square root of 4 is 2, and 2 cubed is 8. So it's 2/3 times 8, which is also 16/3. So there you have it. We were able to do the same region's area by using two different types of iterated integrals. One, the order was dx dy. The other was the order dy dx. Both produce the same results. In terms of simplicity, there's really not a whole lot of difference in it. Computation, I mean, there's a trade-off here. The first part, when we did it in dx dy, we had just polynomials which contain multiple terms, whose integration is pretty straightforward, pretty easy. For the second one, we had to integrate a radical function, but that one also was kind of a little bit easier in the sense that it only had one term to deal with, which computationally makes it easy. So you at least see that there's multiple ways oftentimes to find the areas of these regions.